Yeah, thank you very much for the invitation. Uh, it's an honor that everyone here I'm sure is much more of an expert on scalar curvature than I am, and so it's a little bit intimidating, but I'll try.
Oh,
Uh,
don't worry, Mom.
so um, Okay. The title of my talk is How Hard is the Theorem of Stolz? And I'll spoil the answer to you. It depends. It depends on what you mean by hard. And that's true not only in the trivial way, if you index over all possible meanings of hard, but also if you index over the meanings of hard that I'm actually going to be talking about. Um, so I'll introduce what I mean by hard in a moment, but first I want to state the theorem that I want to analyze, which again, everyone here probably knows better than I do, but I'll state it in the form in which I want to analyze it. So take a simply connected manifold, um, dimension at least 5, and then there are two sub-theorems, one due to Gromov and Lawson, um, which says that if M is not spin, then it always admits a metric of positive scalar curvature. And the other half is due to Stolz, which says that if M is spin, then there's an extra invariant. So it admits a metric of positive scalar curvature if and only if the index of the Dirac operator written alpha m is 0. And so what I want to talk about is um, say you have a very skeptical friend who comes to you with a manifold and says, okay, I know this is simply connected, so I know the topologists say it's going to admit a metric of positive scalar curvature if and only if blah, blah, blah. Well, okay, but can you just give me a metric of positive scalar curvature? How hard can it be? Um, so if someone gives you a manifold, um, how hard is it to produce the positive scalar curvature metric, um, or say how big does this metric have to be, or how complicated in terms of some measure of complexity of the amount of information that you need to describe your manifold. So, one motivation for studying questions like this is one that Shmuel, who's in the audience, has really promoted, is that it somehow, right, you get all these very inexplicit algebraic theorems in topology that you take some topological object and you extract some algebraic invariants, and then you uh, manipulate those invariants and you get out an answer. But it's sort of not clear how geometric is this answer, or could you have found it just by looking, or do you really need or does this algebraic manipulation sort of produce a miracle, right? So if it turns out that the smallest positive scalar curvature metric on your M is way, way more complicated than the original metric you started with, then that somehow makes the topology sound more impressive. And so instead of just waving my hands, let me give some examples of past theorems that use this paradigm. And in part, I've chosen these examples because they're actually going to be useful for the main theorems that I'm talking about today. So in these examples, I'm going to give a topological theorem and then some sort of quantitative statement that says, how hard is it? How hard is this topological theorem? So one example of a topological theorem, this is a corollary of Smale's H-Cobordism theorem, is if you have an n-dimensional hypersurface in a 2n plus 1 ball, or I guess maybe I should call it a disk because it's closed, and n is at least 5. If the sigma is an embedded sphere, then it's actually isotopic to the boundary. So there's no topological information to this embedding. It's always just going to be in the same isotopy class. So from the topological point of view, as long as you know that your surface is the sphere, this is a trivial problem. And now, okay, if you have an embedding, there's a natural way to measure its complexity. Which is you take the thickness of, you thicken it up and you see how far you can thicken before the normal vectors start hitting each other. So but we can measure the complexity by thickness inverse, where right, where thickness is the sup radius of an embedding of a normal neighborhood. And right, okay, so if you have a bound of thickness up to small perturbations, there's only finitely many choices for what your sigma even is. And so then there's a function that given sigma of complexity, say C, there's an isotopy, let's say, I don't know, phi t, such that every phi t of sigma has complexity at most f of c, right? This is just because there are finitely many things you can do. But it turns out, and this is a theorem of Nabotovsky, that f of c grows faster than any computable function. So any function where you can write a computer program that outputs values of that function is going to grow slower than this f of c.
Wait.
So,
This was Novotovsky.
any,
It's Novikov forever. It's Boom Novikov forever. It's what was known before, this trivial corollary of the non-solvability of the word problem, right? So Novotovsky is trivial corollary. In this particular case, yeah, there is nothing of Novotovsky just because finitely many, period. It's not you cannot detect simply connected. And certainly in your
right, exactly. But yes,
but also in your everywhere when it's simply
that
connected, you have to say, you have to cancel off this part. We don't know what simply connected means. You have effectively simply connected, right?
Sure. This is what I'm about to say.
Yeah, but Nabotovsky,
the work of Nabotovsky actually
it has long history in Nabotovsky.
is showing that you can that you can write down this finitely many in a reasonable way that a computer can understand, and it actually turns out to be a lot of work from what I understand.
No, this Kern's triangulation theorem. He apply argument due to Kern's that every such pattern can be canonically triangulated. Come on. No.
Okay.
This is the easy part. There are difficult theorem in Nabotovsky, but this is an easy one. I don't think there is something.
So Misha, this was Nabotovsky's thesis. I think that it's true it's an easy theorem, but I think at the time the thing that was interesting was recognize. So if, for example, one would have assumed that you had a parametrite, an actual embedding of the sphere with a parametrization, then then one has no idea how the complexity grows, right? And all that one knows by the observations you're making is that is some recursive function. I don't think we even know for sure that it's a primitive recursive function, although it surely is, right? But, one doesn't have estimates for that. But what Alex's observation was that, beforehand there were like observations of yours like that for if you have unsolvable word problem, then there are infinitely many closed null homotopic geodesics, things like that. And what Alex brought to the table was the fact that the assumption that something is a sphere, that's also a logical assumption. Okay, right? So, I think you're correct, but I think that the history was that it was sort of, I think it was Alex's observation. But yeah, mathematically, it comes out of whatever, the unsolvability of the triviality problem. Which also, by the way, even though now it looks to us like all of that is the same as the word problem, it was a few years in between.
No, but there was already a theorem by Novikov, of young Novikov, saying that detecting diffeomorphism, homeomorphism, etc., equivalent in this category to the word problem. You see,
right?
Already was done. So, So this point already was handled. And here only the question of triangulation and the standard Kern's triangulation give you this.
There's also epsilon more, which, the fact that you could build the examples so that they're embedded in the sphere, right? There's still a little bit more, but yeah, it's not much more. I agree.
Yeah, so let me summarize what Misha was saying about the idea of the proof of this theorem, where you start with the fact that there's no algorithm even for codimension 1 submanifolds of the disk that can detect whether that, okay, what just happened? Okay, I'm back. Right, whether sigma is actually a sphere or a homology sphere, because you can always compute homology with highly non-trivial pi1. Right. On the other hand, if we had a computable bound on this function, then we could try all possible isotopies, again, up to a small perturbation. And if we didn't find one, right, if we found one, then sigma is a sphere. If not, then pi1 of sigma is non-trivial. And so that's a contradiction. So this is, this is, as Misha pointed out, this is one of the simpler examples of how logic can force these geometric objects to be very large. And so, right, this is maybe an example where algebraic topology does something that looks very impressive. And now I want to give another example where it does something maybe somewhat less impressive. Right, so there's a classification of which smooth manifolds are, I guess, smooth n manifolds are boundaries of an n+1 manifold. Right, so which manifolds are cobordant to each other, which I don't want to discuss, what the invariants actually are. But the question is, if you have a manifold that is null cobordant, that is a boundary, can you find the thing that it's a boundary of? And here, the right notion of complexity, which is probably due to Misha, is you take you look at all possible metrics that are locally nice, that have locally bounded geometry. So what I'm going to mean by that is the sectional curvatures are always between -1 and 1, and the injectivity radius is at least 1. And you take the least volume of such a metric, and this somehow, right, this roughly tells you, how many trivial balls do you need to glue in a trivial way in order to get this manifold. And Misha's conjecture was that if M is a boundary, then you should be able to find a W that it's the boundary of that's not much bigger than M, that's linear in the size of M. And so far, the state of the art is something a little bit weaker than that. So this is a theorem I proved with Shmuel and with Greg Chambers and Dominic Dutter, which says that you can find W with complexity of W. Well, it's bounded by some function of the complexity of M, where this function grows slower than x to the 1 plus epsilon for every epsilon. So for example, it could be something like x times polylog x. That would be an example of a function that satisfies that, but we don't know whether it's a polylog or really anything else. But at least, right, it's pretty close to linear. Okay, so these are the two examples that are going to play a role in our new results. Let me also state one more example just to show you that these are not the only two modalities, right? You can have something that's undecidedly hard, you can have something that's pretty simple, or you can have something that's somewhere in between. So it's a theorem that goes back to Van Kampen. If you have an n-dimensional simplicial complex, it embeds in R2n if and only if a certain obstruction in Z2 equivariant cohomology of the deleted product vanishes. And actually, Van Kampen showed this before cohomology was really defined. So it's kind of impressive that he was able to conceptualize it and write it down. And so Friedman and Kruskal analyzed the complexity of this theorem. And so in terms of the number of simplices of this K, they showed that that certain Ks are exponentially hard to embed, and all Ks that embed are at most exp of n to the 4 hard to embed. So this is an example where the right answer is somewhere on the order of an exponential.
It's a recent paper, yeah? This is quite impressive, yeah.
This is, I think, 2013, or the
2013,
yeah, the preprint is from 2013. Okay, so now I can tell you our theorems. So this is with Shmuel and Zhizhang and Guoliang Yu. I feel like I should change my name to something that starts with a Z. So the first theorem right? Same setup as before. Take a simply connected manifold that admits positive scalar curvature. And let's say it has complexity V in okay, I have my pointer. Complexity in this sense that I discussed before. Then it admits a bounded geometry positive scalar curvature metric of volume some kind of exponential in V to the slightly more than squared. So, okay, we have no evidence that this is anywhere near sharp, right? We don't know that the answer isn't linear. We just have this exponential upper bound. But it's something. And right, okay, so this metric exists, but if you start at your original metric and try to walk to this metric, that's going to be very hard. So, right, let's say, in addition, instead of the Gromov-Lawson case, we're in the Stolz case. So, then for any metric on M, this is a preamble and not the theorem. Right, for any metric, there's a path through, let's say, GT through metrics of bounded geometry. To a positive scalar curvature metric. So this is, again, just because there are finitely many options. Sorry, such that each of the intermediate metrics has volume at most, let's say, Fm of V. So my function depends on the manifold I started with. And it exists because there are finitely many options. However, this function can't be bounded by any computable function. So let me right, you can, at this point, you can probably guess how at least, what the outline of the proof of this second theorem should be, but I want to give that outline and then point out how there's some tension actually with the first theorem. So the idea is that M has lots of evil twins that don't have positive scalar curvature, that have complicated pi1, and that pi1 obstructs positive scalar curvature in some way. And it's undecidable whether a manifold that you just hand to me is M or one of its evil twins.
And indeed, you need to be spin.
Yes, for this one, we don't know. Yeah, for this one, we know how to do it in the non-spin case. Or sorry, in the spin case, we don't know how to do it in the non-spin.
That's fun, yeah.
Yeah, so if this function was bounded, right, again, it's the same logic as in the Nobutovsky theorem. If f was bounded by a computable function of v, then we could test all possible GTs, right? All possible deformations through the space of metrics. And if we succeed in finding a metric of positive scalar curvature, then we have M. Otherwise, we have not M.
So it concerns unspecified metric of positive curvature in the end, not the one we constructed given to you, right?
Sorry?
So my question is, so in particular, if you have two manifolds of positive scalar curvature, then this isotopy may be of this kind. Or
yes.
any metric, no matter starting from any metric, always there is a kind of far-lying metric of positive scalar curvature.
So the setup is we start with any metric, and we're trying to get to a metric of positive scalar curvature, the closest one.
So the conclusion, the point is that positive scalar curvature kind of makes it simple, right? And enough to be kind of in contrast with algorithmic with fundamental group, right? It's kind of more like simply connected, right?
Right. Yes.
It's quite remarkable thing, geometrically very remarkable thing, yeah. Right. It says the manifold of positive scalar curvature kind of simple, logically.
Yeah. So testing whether your given metric has positive scalar curvature is testable, right? In general, right? So let me point out the contrast with theorem one, right? Why doesn't the same thing happen? For theorem one, why doesn't this argument contradict theorem one? And the answer is that the construction that we do produces a a manifold of positive scalar curvature which happens to be M if the original M was simply connected.
It was
Right? Otherwise,
simply connected.
yeah, so we're actually relying on simply connected here.
Uh-huh.
Otherwise, we end up with basically a positive scalar curvature metric on the plus construction of M.
I see. Uh-huh.
Right. So yeah, it's not true that positive scalar curvature that having positive scalar curvature is geometrically simple, right? And that's essentially what theorem 2 is saying. However, since the original theorems of Gromov, Lawson, and Stolz go through Cobordism, we can produce a cobordant manifold of positive scalar curvature. And if the original thing happened to be simply connected, then it's the same manifold.
Because there is another way to measure this distance between two manifolds, not only by the path and how much you have to distort it, but by just looking, say, by Lipschitz maps. If you use this metric, do you have comparable estimates?
I think you get the same thing, right? As long as you have something that testably relates the original manifold, the original metric to the metric of positive scalar curvature. For example, a by Lipschitz map, right? Then you can test all possible by Lipschitz maps, and then you would recover whether the original manifold was M or something with fundamental group that's hard to distinguish from M.
Yeah, right. So I think that the answer to Misha's question is that if you use the by Lipschitz thing to measure distance, then the distance would be, right, would be very, very large, right? I mean,
yeah, sorry,
right,
that's what I meant.
You don't need to look at the paths.
Yeah.
Okay, so you can construct on a sphere of metric of positive scalar curvature, and they very far from the standard metric, Lipschitz wise.
Yes.
Yes. Yeah.
Because this surgery, which make you positive scalar curvature, kind of independent on the surgery involved in the 1 and 2 handles, right?
Right. Yes. So this is
you do it by high dimensional handle. You don't touch 2 handles, so to speak.
Yeah.
Right?
So let me.
Yeah. So for example, all the Novikov
give some of the ideas of the proof of theorem 1, and basically the fact that you have to avoid codimension 1 and 2 handles. That's what leads to the extra exponential.
Mm-hmm.
So yeah, let me recall for everyone how these theorems of Stolz and Gromov-Lawson are proved. So you start with just looking at the Cobordism classes of manifolds with this property, right? And you see that each of these Cobordism classes has a representative with positive scalar curvature. So there's some manifold in the Cobordism class that has positive scalar curvature. And then the second lemma, again, this one goes back far in the past, right? This is a basic fact about handle attachments. If you have two simply connected manifolds that are cobordant, then the cobordism, right? So if you have a cobordism, you can sort of break it up into a bunch of handle attachments. So and in the simply connected case, you can get away with attaching only handles of codimension at least 3. Sorry. So, right, this is a dk plus 1. This is a dn minus k, and where k is at least 3. And then the big contribution, or one of the big contributions of Gromov and Lawson, was to show that there's a way to attach these handles so that if the if one side has positive scalar curvature, then so does the other side. And in fact, there's an improvement to this, which I think is due to Geyer, which is that you can make the whole cobordism have positive scalar curvature. Okay, so this is an outline that now we want to try to do.
I only interrupt you for correctness sake. Sean Yao also proved that, yeah, at the same time.
Yes.
It's also Sean Yao.
Yeah, thanks. Yeah, so we have this outline, and now we want to make the different steps quantitative. So to make step 1 quantitative, right, we want to say that these representatives with positive scalar curvature, that they're not too big, and this is easy enough. because, right, the Cobordism class depends on, well, it depends on Pontryagin classes, which are linear in the complexity and some finite stuff. And so you can find a manifold N cobordant to M with positive scalar curvature and about the same volume. Okay, and then once we've constructed a cobordism, so once we've done step 2 in a quantitative way, so we bound how many handles we attach and how complicated those handle attachments are. Then step 3 is you need to do the positive scalar curvature thing in a careful way. So right, attach all K handles at the same time with positive scalar curvature and a linear increase in volume. And so maybe the most interesting, or at least, that part, yeah, I know less about how to construct metrics in a careful way, so I'm not going to talk more about it. So this constructing the actual cobordism is what I want to actually talk about. So remember, we already have a cobordism theorem. So the theorem with Greg and Dominic and Shmuel gives us a cobordism between N and M of a volume of v to the 1 plus epsilon. And we can actually, first of all, we can make this cobordism spin. That's not in our paper, but it's not any more difficult than the original argument. And secondly, we can triangulate it. Right, so there's a smooth triangulation with this many simplices and bounded geometry in the sense that there's at most some constant depending only on the dimension, simplices meeting at a vertex. Right, and this triangulation gives us a nice handle decomposition. Right, we can, I don't know, here's my triangulation, and I can make the vertices into 0 handles and the edges into 1 handles, and so on. And so the problem that we need to solve is how do you get rid of codimension 1 and 2 handles? And in fact, right, before we even talk about that, right, a cobordism that doesn't have codimension 1 and 2 handles is necessarily simply connected itself. This cobordism that's produced by this 4-author theorem, there's no guarantee that it'll be simply connected at all. So if we want to get rid of codimension 1 and 2 handles, we first have to make the whole thing simply connected. And basically, we need to fill all the loops that might give you pi1. We need to add 2 handles that kill them. So how do you do this? Well, you take the 1 skeleton, and you find a spanning tree, or that's not a tree, this is a tree. And then, right, every edge that's not in your spanning tree corresponds to a loop. For example, right, in the spanning tree I drew, this edge gives you this loop. So there are, how many edges are there? Well, approximately O of the volume. And the length of each loop is also O of the volume. So just attaching these handles, just attaching these 2 handles squares your volume. Right, so now we're at, if you're keeping track, we're now at v to the 2 plus epsilon rather than v to the 1 plus epsilon. And now, for the rest, I'm just going to draw a picture, right? So let's just say this simply connected thing that we got in step 1 is still called W. So here's my W. It goes from N to M. And now I just, I just take all the low codimension handles and I just don't add them. So I got something like this, right? I got some M prime that sits in the middle. and let's say I have a W prime on this side, which has no codimension 1 or 2 handles. And then on this side, I have something that I might call W complement. It's the complement of W prime and W. And right, everything here is simply connected. So if we look at H2 of W complement relative to M, right, by Hurevich, this is the same thing as pi 2. So we can kill it by adding 3 handles. And the fact that we only added 1 and 2 handles to make M prime from M means that, right, the higher relative homology is going to be 0 up to, the complementary dimensions. And so by adding 3 handles to W complement, we actually get W complement to be an H cobordism and therefore a cylinder. Right, so imagine, right, gluing in these 3 handles. Now, the resulting manifold on this side is actually just M. Right, but the point is, when we glued these handles on, they're just being glued to M prime. They didn't see that they're going on this side rather than on this side. So if we glue them on this side, then we were adding some 3 handles to W prime, right? So W prime plus 3 handles is a cobordism from M to M. And okay, but the point is, right, these 3 handles is where we get the exponential, because this 2-dimensional there we go. This 2-dimensional homology is right. If you want to find a basis for it, that basis might have to have elements of exponential size, and so like the coefficients of certain simplices are exponential. So if we want to glue in these 3 handles, they have to wind around a lot of times, and so that's where we get the exponential blow up in volume. All right, I'll stop here. Thank you very much.
Thank you very much for your talk. Can you just explain this very last point again before you stop your talk? So I understood the side where you made it a cylinder, and then what was this last point about W prime?
So the the last point was about, right, we're attaching these three handles to make this side of W prime actually diffeomorphic to M.
Right.
And the point is, okay, let me give a simple example. If you take, I'm just going to build you a two complex where you start with a disk and then you do a degree two cylinder, a mapping cylinder of a degree two map, and then you do another mapping cylinder of a degree two map, and you do this n times, and then on the other end, you close the lid of the telescope. So if you want a generator of H2 of this object, this CW complex, it's going to have degree 2 to the n, or its coefficient on one of the lids is going to be 2 to the n. And it's not hard to embed such an object in a manifold and get a situation where any representative of your homology class is going to be exponentially large.
Okay.
But you have to all the time assume a dimension at least 5, right?
Yes.
Dimension 4 it will not work. Why I understand that morally? So if you have kind of this potential pathology, it's simply connected manifold, but looks not simply connected because there are suspicious loops. You just take these loops and then you just kill them and kill them again, so you don't change topology. And now we have positive scalar curvature, but now it's effectively simply connected.
Right?
Yeah. Right.
Yes,
You always
exactly.
make everything effectively simply connected. Introducing phi 2 with positive scalar curvature as you want, and then kill it back, and then you need dimension.
Yes, that's exactly what we're doing.
But don't you need dimension 6? Yeah, 5 is enough.
I think 5 is enough.
5 is enough. Yeah,
Will you have?
Just accounting for dimension. 5 is enough. Okay.
Yeah, but but there's, by the way, Misha, there's still right. So there's a basic topology problem, by the way, in the question that you asked, which is just if I take a manifold that doesn't know it's simply connected, right? I mean, it looks simply connected because H1 is 0, right? So then, right, there's this H cobordism to the thing that you just described, that, right? I mean, when you add those two handles and three handles, right, you build a semi-H cobordism to something which is effectively simply connected. So the question is, so there's a cobordism that's like volume to the 1 plus epsilon. But is there an H cobord? The smallest H cobordism we know is exponential in volume. Right. So that's sort of an interesting problem there, right? I mean, when you want to get rid of the logical complexity, and you can by trivial topological construction. So how hard are they?
Okay, yeah, I just indeed, yeah, there is some subtle point here. Yes, I agree.